We will now discuss the fundamental theorem of calculus. So what is the fundamental theorem of calculus? If a function f of x is continuous on the interval, closed interval, a comma b, and capital F of x is an antiderivative of f of x, then the following is true. The integral from a to b of f of x dx will be equal to f of b minus f of a. And the notation that we use once we evaluate the antiderivative, and we use the notation of a line where we look at a to b, and this demonstrates f of b minus f of a. Now a here is called the lower limit of the integral, and b is called the upper limit. Now it's important to notice here that when you plug in, after you take the antiderivative, you first plug in b and then you plug in a and you subtract the two. Now, what does this actually mean? What are we finding? So for example, if you were looking at f of x is equal to x squared, and you would evaluate the integral from, say, 0 to 2 of x squared dx, and we would look at it graphically and say this was 2 and this was 4, what you are finding when you're evaluating the definite integral is you're actually finding the area under the curve. So this would be what you are finding. So the first question I have here is, why is there not a plus c anymore? What happened to the plus c that we kept using in an indefinite integral? Now the reason for that is, imagine that you have the antiderivative f of x. So you would have some part here that would involve x's, and then you would have the plus c. So when you would plug in f of a, all of these x's would turn into a, so you would have here involve the a's plus c. And when you do f of b, you would have this part here, the b's would replace the x's, so this would involve the b's, and then you would still have plus c. But because you're doing f of b minus f of a, your c's are going to cancel out because of the subtraction here, right? So you're going to have a part here that involves the b's plus c minus the part here that involves the a's plus c, and when you distribute the negative, the c's would cancel. So this is why we no longer have to write the plus c, because both of them would have it, so they would cancel out. Okay, so now we're going to evaluate the definite integrals. So I have a couple here. So let's apply the fundamental theorem of calculus. So to evaluate this definite integral, I use the theorem. So first I will take my antiderivative of 2x. So it will be 2x, add 2, divide by the new power. And I use this notation that I want to evaluate from -1 to 2. Now this is going to simplify to x squared from -1 to 2. First I plug in my upper limit, and I subtract that from my lower limit. So that would be 2 squared minus -1 squared, and when I evaluate, I will get 4 minus a positive 1, so it is 3. So again, what I found here is that the area under the curve of 2x, which is a line, from -1 to 2 would be 3. All right, let's do another one. So the next one here, before I evaluate, I'm going to change this to x to -2. Now I'm going to take the definite integral. So first the derivative, the antiderivative, my apologies. So I'm going to add 1 and divide by the new power. This is from 2 to 5. So this gives me -1 over x from 2 to 5. So I'm going to have -1/5 minus a -1/2. So be careful there with those double negatives. We use parentheses. So I'm going to have -1/5 plus 1/2. And here I can do a common denominator, or you can just use your calculator. So this is going to give me, if in decimal form, it would be maybe a little easier. This is going to be -0.2 plus a positive 0.5, which will give me a positive 0.3. Or you can do it in fraction, but you have to do a common denominator. So when you do that, it's going to give us a common denominator of 10. So I'm going to have negative 2 over 10 plus 5 over 10, which would give me 3/10, which is 0.3. So both is fine. Okay, let's take a look at the next one. So I'm taking the definite integral from 0 to 2 of 3e to the x dx. So first I'm going to evaluate the 3e to the x, the antiderivative, which is going to be 3e to the x from 0 to 2. First I will plug in my upper limit, and I will subtract that from my lower limit. When I do this, it's going to be 3e squared minus 3e to the 0 is 1. So this is 3e squared minus 3. And I'm going to leave my answer like this. I don't want to find a decimal. With the e is perfectly okay. All right, let's take a look at the next one. So now the integral, the function inside the integral has gotten a little bit larger, but it's okay. Because it's plus and minus, we just take the antiderivative of each. So I'm going to have 4x to the 4th over 4 minus 6x cubed over 3 plus 10x squared over 2. I add 1 and divide by the new power, and I'm evaluating from the negative 2 to 3. Now before I plug in, I like to simplify. So that's going to give me, and I'm going to use parentheses here to denote that I'm taking it on all of it. So I'm going to have x to the 4th minus 2x cubed plus 5x squared from negative 2 to 3. So here parentheses are really important. So first I'm going to plug in 3. So I'm going to have 3 to the 4th minus 2 times 3 cubed plus 5 times 3 squared minus parentheses negative 2 to the 4th minus 2 negative 2 cubed plus 5 times negative 2 squared. And now we need to evaluate all of this. So this is going to give me an 81 minus 3 cubed is 27. 27 times 2 is 54. Plus 3 squared is 9. 9 times 5 is 45. Minus negative 2 to the 4th will be 16. This will give me negative 8. So this will be a positive 16 again. This is going to be a positive 4 times 5 will be 20. So when we combine all of that, that's going to give us a 72 minus 52, which will give us a final answer of 20. Okay, let's take a look at one more. So we have the definite integral from 5 to 5 of 32x times x squared plus 1 to the 7th. So to be able to use the power rule here, because this is to the 7th power, I would literally need to expand x squared plus 1 7 times. So you should be like, wow, that's going to take forever, which it would. But actually, we don't need that. And the trick comes that the lower bound and the upper bound are exactly the same. So imagine that you do take the antiderivative of this, and we let it label some sort of f of x. But then you would be evaluating that from 5 to 5, which means that you would do f of 5 minus f of 5. So because the bounds are the same, it actually just ends up being 0. You don't need to know the antiderivative because the bounds are the same, so you have gone absolutely nowhere.